problem. So for 5.1, it's target on the spring and mass system, okay, and initial value problem. So the force from the spring itself, from the fixed the fixed supporter that the spring attached to it, and also from the external force. So the sum of all force here based on the Newton's law, like F equals ma. So F of s, you guys see the screen, okay? Let me expand it a little bit here. Okay. So we talk about forming modeling the differential equations to describe the motion of the spring or the position of the mass that attached to the end of the spring. Okay. And the spring is attached to some like the fixed support or some dashboard. And for our case, that based on Seuss textbook, is the spring attached to the fixed, okay, the fixed support there, and the mass attached to the other end of the spring. So the force will come from the force based on the spring. So it's from the Hooke's law that the force is stretched or compressed the spring by some distance s is proportional to that distance, or the formula that you are familiar with, say back in Calc 2 or some in physics applications, the F equals k times s. K is the constant factor or the spring factor, the spring constant. Okay, and with the mass that attached to the end of the spring, so going to be the position that's affected by the mass, which is mg, and then pull it down to the position x, and also like the mass itself that's based on the spring constant that's stretch it out away from the equilibrium position by the s. So the k times the x plus s here is from the spring, and the mg is from the mass of the is from the weight from the mass that attached to the spring. So this portion is the force based on the spring itself with the mass attached to it. And the other one, the FR, this one is called like fractional force, or the one that based on the depth, what is called the friction based on the fixed supporter here that the spring attached to it. And the other one, the FE, or the external force, this one, it could be from something or some external force that maybe some extra force that pull the spring down in addition to the force that from the from the spring and the mass itself based on the gravity. So the sum of these three pieces of the force equals the sum is equals the force that based on the Newton's law. Okay, so the frictional force here is the force that's proportional to the acceleration of the spring, because it's about the spring and the fixed supporter. So all three pieces all together here, we can get the differential equation, the second order, that represents the position of the mass attached to the spring at the time t. So for each one, let me explain a little bit more. Like the one that's from the spring, like negative kx, negative ks, the sign negative because it's go in the opposite direction. Okay, and the mg, as you see, like one is pulling up, one is coming down, so kind of opposite direction. And also the frictional force is in the opposite direction, kind of go away from it, and the external force that's an add-on to it. So with these three portions of the force together, that's form the differential equation. Okay, that's from the Newton's law, like F equals ma. A is the acceleration, so m the x double prime plus the beta. Beta is the damping force based on the fixed supporter. The K is the spring constant. So when you rearrange a term, all terms are the negative on the right hand side to go over to the left hand side. So it becomes the three terms that you are familiar with, I'm sure. It's about um, the second order differential equation. So we have m x double prime plus the beta x prime plus k times x equals f of t. If f of t is not zero, so we have the non-homogeneous equation. If f of t is zero, so we have homogeneous. So the case that we have the damping force effect to the spring, so the beta is not zero, so we have the middle term or the term that involving the velocity or the xdt. But the k will always there because this is the problem involving the spring. So the k or the spring constant will be part of the problem. So either like have the f term, which is the external force, or no f term. If no f term, so that means it's a free motion. Free motion, that means f at t is zero. Then that means the beta is not zero. Undamped, the beta is zero, or no frictional force. Okay, this is the full version of the second order differential equation representing the motion of the mass that attached to the spring. That's what we're gonna work on for 5.1. Okay, and with these differential equations, the position of the mass at the point t. So at for the t equals zero or the initial position, if it's starting at the equilibrium position, the x at zero gonna be zero. Okay, the sign of the initial condition depends on the position. For the initial position of the x at zero, it's zero at the equilibrium position. If the initial position positive, that means it's the quantity x subscript 0 below the equilibrium position because it's stretching, so it's going down, so it's going away from the equilibrium position, so it's below. So this is key term that you are going to use to identify the plus minus sign of the initial condition. Okay, and if the x at 0 is negative, that means it's compressed, so it's pushed up at the like above the equilibrium position. So above the sign negative, below the sign positive for the initial position or initial condition. And for the initial velocity or the x prime, if it released from the rest, the x prime is zero. If it's in the downward velocity, that means it's going down. Again, going down, that means going away from the equilibrium position. So that means it has like positive direction or positive number. So x prime positive, that means it's going in the downward velocity. That means the slope is going to be slope positive, but the direction is going opposite way for the graph. When we get to the end of each problem, I'll explain using the graph based on the description of the problem. Okay, and if x prime is negative, the motion is about upward velocity. So the sign, it looks like opposite to what we read from the description. So below positive, above negative, downward positive, upward negative.